This is a quick explainer video. We're transitioning to talking about significance testing, and significance testing is unintuitive, but it it's very logical. It arises from the HCs that we've learned so far. So if you know about descriptive stats, distributions, probability, confidence intervals, you could infer the existence of significance testing. But I want to give an example of it and just talk through how it works. I think the next several lessons are great at talking about elements of significance testing, like type 1, type 2 errors, of teaching how to calculate significance, whether or not a difference in mean test is significant, but it's hard to a little bit to understand what is going on. And so I just wanted to make this every year. I feel like we kind of want students to infer the existence of this, but then if they don't, and then we just start explaining other things, they never get it. And here's a very, simple way to understand significance testing. I'm going to give an example, a concrete example here. You've got to imagine you have a population distribution that's really simple. We're just going to roll a 6-sided die. So this should be pretty familiar. We have a nice uniform distribution. The population is this distribution is this uniform distribution. It is 1/6 tall, and then has six units wide. So that obviously sums to 1. So here's our population distribution. And we are going to, so this is the population mean is right here at 3.5. The population standard deviation, I'm not going to calculate it, but I think it's 1.5, about like that. And so you're going to roll a die, and you're going to get a standard deviation that looks like this. This is the basic, that should be pretty clear. All right, so now we're going to sample. Actually, this might be a record at some point. So we're going to sample from that distribution. And when we sample, we get a list of 1 numbers. So let's say our first sample is a 1. All right, let's draw a graph down here of our sample mean. Here's our sample mean. And here is our sample size on the bottom here. So we'll call this N. And then sample size 1. Okay, our sample mean after 1 trial here, we just happen to get is 1. Okay, great. Let's do another trial. Say now we roll a 2, right? Now our sample mean is going to increase. So when N equals 2, our sample mean is now, so here's 1. So now here's 2, 3, 6. Right. So now our sample mean, if after 2 trials, is 1.5. Right, so our sample mean's gone up. Cool. We do another trial. And now let's say we roll a 6, right? Well, that makes our sample mean jump all the way up to 3. Right? So we've done 3 trials, now our sample mean is a 3. We're going to repeat this again. Let's do a 4th trial. Oh, we get another 6. Now our sample mean is going to jump up to 4. I hope this is clear. Our sample mean here is 1. And then here it's going to be the sum of 1 plus 2 over 2. And then this, after trial 3, it's going to be 1 plus 2 plus 6 over 3. And then after 4, it's going to be 1 plus 2 plus 6 over 4, and so on. So we're going up and down. As we go on, this sample mean's going to bounce around. It'll go up. Maybe it will roll some high numbers. Maybe we'll roll some low numbers. It'll go down. But over a long enough time, it's going to bounce around less and less because we are adding up more and more numbers over here. So each number is making a smaller contribution to the sample mean, because look, here we had just 1 number, now there's 2, now there's 3, now there's 4. The list of numbers that we're adding up is getting longer and longer, so our sample mean is converging. And eventually, if N equals infinity out here, this would converge to 3.5, if this is a fair die. Right? So over time, first we have these big jumps, but then over time, as this goes on and on, this kind of smooths down, the jumps get smaller, and we end up at 3.5. Okay, great. I clean this up a little bit here so that can have a nice thing to draw on here. It's bouncing around, going up a little, going down a little, but over time, the ups and the downs get smaller, and then we end up with a nice smooth 3.5. All right, great. And out here, we're going to have the idea is out here at about when N equals about 30, we should be pretty close to 3.5. That's a reasonable rule of thumb. You'll have converged there. All right, but the reason that this, of course, converges this way is that the distribution of the sample mean as we get more and more, approaches a normal distribution. So this is now we're looking at the estimated sample mean here, and this is going to get really close to 3.5 is going to be at the middle of this normal distribution. As we roll more and more dice, we're going to converge closer and closer to that middle of the normal distribution. The odds of us being out here in the tails and therefore not having a sample mean close to 3.5, having a sample mean that's far from 3.5, go down. Look how little mass there is in this tail. There's a lot of mass here at the middle of the distribution. We know that we're going to get a normal distribution when we average a bunch of numbers. And therefore, we know we're going to converge to this middle number when we average a bunch of numbers. And the probability of us being out in the tails is going to go down and down as we average a bunch of numbers. Okay. This should all be pretty familiar. The one other fun thing you can do is you could say, oh yeah, I could calculate. Also, I know how to calculate a confidence interval on this. And after 2 trials, my confidence interval here, I'm not going to go through the trouble of calculating it. At here, I could draw it around here like this. It's okay. So after 2 trials, my confidence interval looks like this. It's a pretty wide confidence interval. After 3 trials, it's going to get a little smaller. Say the mean is somewhere in here. The mean is somewhere in here. I think it's 95% chance the mean somewhere in here. 95% chance the mean somewhere in here. To this trial, it's okay. 95% chance the mean somewhere in here. As we go along, each time we roll a die again, each time our n goes up, I already screwed up. Die again, each time our n goes up, and we draw this confidence interval around the sample mean. That confidence interval is going to get a little smaller every time, and a little smaller every time, until by the time we get out here, it gets very tight. Really certain. We have this really tight confidence interval. Of course, out here at infinity, the confidence interval is 0, right? So we say 3.5, that's the sample mean. Okay. As we're doing this, you can imagine each one of these confidence intervals is a map of what's going on over here. It's a visualization of this distribution. Imagine we're looking at this distribution from the top, right? Now we see the averages here. We see the tails sloping off to the side there in red. So we're looking at, imagine this is the distribution that we're looking at over here. And we're just seeing it from the top. Here's the mean, right? The mean is right here in the middle. And then we're seeing the tails of this normal distribution that we're constructing. That's our confidence interval. That's represented by our confidence interval. So as we're rolling this die, so now think about what we're doing. Rolling this die over and over again. We know the population mean looks like this. We're rolling it a bunch of times. The more times we roll it, the more confident we are that the average of that sample is close to the average of the population. The tails of our confidence interval are getting smaller and smaller. Our confidence interval is getting tighter and tighter around that mean. And we have this distribution of the sample means where the average is converging to this 3.5 of the population mean. Okay, now we're set up to do a significance test. Now we're ready to actually infer how to do a significance test from all of this stuff. Okay, so the last thing that you know how to do is you can actually measure distances on this distribution using a z-score. You know how to do things like, oh, okay, I get with a z-score of 2, or 1.96. That is a z-score of 1.96. Actually, let me change colors again here. Let me do the text too. Let's go to blue. And you know that that corresponds to standard error of 2. So say this properly. So z-score of 1.96, 2 standard deviations essentially above the mean. That z-score is going to correspond to 95% of the mass of this distribution. So something like, over here. This little bit here is still white. If we're being precise, this little bit over here is not filled in. So we have integrated, we're adding up the mass of this distribution. A z-score is just an integral that sums up the mass over here, just like we could sum up the mass by adding up 5 of these blocks up here to get 5/6 of this population distribution. The z-score is just a mathematical function that integrates, that finds the area here. When you have a z-score that's 1.96, it's at this point, about a little less than 2 standard deviations above the mean. Then you know that, and corresponding 1.96 on this side, then you know that 95% of the mass of that probability distribution is there. So the area is 0.95. And it's not just 95 that's important here, you could do this for any z-score. For any z-score, you can tell me how much area corresponds, how much area is to the left of that z-score by using the cumulative distribution function. Actually, I'll just do it over here, stats dot CDF, and you give me a z-score, and you give me, or actually, you give me the mean z-score. Give me a mean standard deviation z-score, and that'll give me the amount of area there. Okay, so far so good. Okay, so now your friend comes along to you, and they hand you another die. Let's do this in green. And they say, I think this die isn't fair. I think it rolls 2s more often than normal. They say, I think that there's maybe the distribution looks like this, where you roll twice as many 2s as you should. The person who's playing dice with them, the person who's playing dice with your friend says, no, this is a fair die. It's just normal. It has a uniform, I should be careful with the word normal. It has a uniform distribution that looks like this. Okay, so we got two alternative hypotheses here. Okay, the null hypothesis over here, okay, so the null hypothesis says this is a normal die. It rolls just like any other die. It follows these rules up here. This is what we expect to see when we roll this die is everything at the top up here. So the null hypothesis says, if you roll this die, you will get all of the stuff we just talked about. You will generate a list of numbers. That list of numbers, the average will converge to 3.5. It will look like this. The population distribution looks like this. The curve for the sample mean would look like this. You would be able to calculate a normal distribution on that sample mean. That's what the null hypothesis says. It says this is what's going to happen. The alternative hypothesis, in this case, makes a specific claim about it's going to roll more 2s. But really, the alternative hypothesis could just say, something else will happen. What will happen? Well, okay, so who's right? The friend who thinks that this is an unfair die, or the friend who thinks that this is just a fair die, right? Okay, what you could do then, you could work this out. You could do it, work this out with significance testing. The way that you do that is you say, okay, look, if this friend is right, then when we roll the die, this will happen. If this friend is right, then when we roll the die, the mean will not converge to 3.5. We'll roll the die a bunch of times. The mean will bounce around like this. The confidence interval will bounce around. But over time, that confidence interval will get small, and that mean should get closer and closer to 3.5. At some point, if the confidence interval, imagine we roll this a bunch of times. So imagine that we do exactly that. So I'm going to do this. Okay, so this is our second die. This is our unfair die. Actually, let's draw our unfair dies curve here in purple. So we're going to get the sample mean of this unfair die. Unfair die. Unfair question mark. Maybe it's unfair, maybe it's not. We don't know. Okay, and then down here, we're going to have 1 roll, 2 rolls, ... all the way out to n equals infinity rolls. And we're going to plot this die. Okay, so once again, we roll it, let's say we get a 4. So our sample mean starts out at a 4. Okay, then we roll a 6, our sample mean goes up to a 5. Then we roll a 1, so our sample mean drops down here. So we have these jumps, and initially maybe we roll a few. Actually, can't move that fast. Hang on, let me erase. I'm getting sloppy. So it jumps up. Get myself a little more real estate here. Yeah. Okay, so it's jumping around, goes a little low, gets a little higher, goes a little low, gets a little higher. All right, and let's go ahead and draw our confidence intervals. So this one's going to start out really big. Again, I'm not really calculating these. Still pretty big. Contracting down a little bit. Yeah, a little bit smaller still. Getting smaller. As we roll the die, we get a better and better estimate of what the mean is. getting smaller, getting smaller. Okay, as we get out here to n equals infinity. But wait, at some point, something interesting happens. So here, is our 3.5 mean, right? That's the line for 3.5, say. And lo and behold, look what just happened. So as we rolled the die more and more, as that confidence interval got smaller and smaller, we just rolled the die enough times that the 95% confidence interval for this purple die, for this null hypothesis, for this new die, this one down here, no longer contains the value of 3.5, right? So we rolled it. And now this confidence interval where we think the mean is, where we're 95% confidence that the mean is in that range, has just gotten to the point where now it doesn't include this mean that we thought we were going to get. And so this original die, which had a mean of 3.5, we were able to test it, right? Now, look, it's getting closer and closer until the mean of 3.5. It's always, the confidence interval is, usually containing it. And then as you go out here more and more, you get out to the point where now the confidence interval contains it and it lies right on top of the mean. So you're like, oh yeah, this is a regular die. So this die is regular. No. Confirmed. Or supported. We've gathered evidence for the null hypothesis here. But this unfair die, look, now we've gathered evidence against. Right? This is how significance testing works. You can gather evidence for or against the idea that this die matches some distribution. You say, okay, so I know that if I rolled this die, I would get these long-running averages. These long-running averages would approach the sample mean would approach the population mean. I could draw a confidence interval where I could say I'm 95% certain that the sample mean is in this interval, right? Or 95% of the time the sample mean will fall in this interval. And then I'm estimating that from the way this normal distribution, which it's guaranteed to appear due to the central limit theorem, is going to describe the average of this rolling the die. But here, when I did that same procedure, when I did the same thing, look, lo and behold, now the sample mean or the population mean isn't within the range of that confidence interval on the sample mean, which means that I bet the sample mean is different on this die. And I haven't confirmed that my friend is right. I don't know. My friend said, I think it rolls more twos than usual. I don't know for sure if that's why. I could go in here and look at the number of twos and try to work that out. I could test a narrower hypothesis. Are there more twos than you would expect? That's something we'll save for later. But what I can confirm is, hey, it doesn't look like it's a fair die. It doesn't look like it's a normal die. What does it do exactly? Let's test that later on. Let's save that for a future lesson. But what I can say is, it's not a fair die. This is what I think you should have in your head. Imagine this picture when you're thinking about significance testing. You're going to be doing you're going to look at a big list of data. You're going to do repeated sampling. You're going to find the average, which should converge to this normal distribution around the population mean. You're going to be able to draw the width of that normal distribution in your confidence interval. And you're going to watch it contract and contract. And at some point, with enough samples, with enough data, and usually to be fair, we usually get all the data at once. It's usually not this curve where it's like we're watching it contract. I just think this is a useful way to understand what's going on. You'll get a bunch of it and you'll just draw this small interval. You'll really be out here. But you'll do that sample and you'll say, hey, this confidence interval that I'm constructing around my sample mean does not contain the population mean that I thought I would get. And so that means that something's going on here. You don't know exactly what, and we'll talk about figuring out ways to figure out exactly what later on. What you can say is, I'm pretty certain that this distance here is greater than you would expect. It's greater than you would expect the mean to fall within. And so I don't think the odds of either we're in one of two things could be true. We could be in that 5% case where the population mean falls outside my confidence interval, or the population mean is different than what I expected. So those are the two things that could be true, right? If you're worried about 5%, of course, you can just gather more data. You can make it 99%. You can make it 100, 1 in a billion. DNA evidence is done to that level. It's 1 in a billion chance of this being someone other than the suspect. So you could just keep gathering more samples, get this confidence interval smaller and smaller until you're really confident. It's really unlikely you're either in that 1 in a billion case or something's fishy. And so that's how significance testing works. That is the guts of it. We're going to teach you a lot of things about it, like type 1, type 2 error rates. That has to do with whether we're in this tail or over in this tail. You're comparing different directions that you could be off in. We're going to do means testing, which is to say, we're going to define how big this gap needs to be before that expected mean and your observed mean are too different, right? So we're going to talk about all those sorts of things. But for now, just think about it in this framework. It's, hey, I know that I could get an estimate of where the mean is. And if that mean falls outside that range that I think is reasonable of that estimate, something is probably fishy. Great. So this should be, I hope this was helpful. I hope this frames that question a little bit.